Today's presentation is, like all of the other ones, being recorded. It's going to be available on YouTube, and that does mean that everything you say when we open up the lines at the end to invite questions, plus anything you type into the chat window is going to be recorded, and there will be attribution to it. And with the thumbs up, I can see that Steve is ready to go, which hopefully means that the audio is working too. Steve, do you want to just give us a quick hello so we can check your volume?
Yes. Now, how does that sound?
That sounds perfect. So at this point, I will fade myself into the background. Steve, your slides are up and we are recording, so we are ready to go, and I will pass it over to you.
Okay. I'm letting you know that people here at the conference have indicated that they wish to attend this meeting. However, lunch just began about 25 minutes ago, so that means that, well, people will be trickling in, yes. My speakerphone is inadequate, I think, for everybody to hear. So, right, other people will need to call in on their telephones as they come in, and in such a case, I'll just go ahead and plug in my headset. Right. I think we're at the point now that we can begin and then allow people to filter in as they wish. Now, as we all know, this webinar is being held because it's part of our astrobiology strategy, and we are tasked with putting together information that will be incorporated into an omnibus white paper that gives instruction and advice and so on and perspective on what we'll be working on for the next 10 years within the Astrobiology Institute. Now, this document that you have posted up in front of you is obviously a working document because that's the working title there, but I'm going to then go to the next slide there. And so this you'll see at the top here, I press the pointer, there's the pointer. Now, of course, there's the topic that we're discussing right now. How does Earth's earliest rock record inform us about the origin of life? And something I want to begin with is a very strong caveat that this document doesn't do an adequate job, I think, in discussing the geological record that is, say, from the middle part of Earth history that is of interest to astrobiologists, specifically the time about the rise of oxygen and the stabilization of continents and so on. So I acknowledge that in this, and just wanted to let you know that this is one of the important things that the document needs input from you, the community, about what is missing. Now, the next slide here, it says something about time and process preserved in solids. And the preamble to that is that there's this idea that it's solid planetary bodies that are needed to accumulate the ingredients for life. And if anybody has an objection to that, I'd like to hear it now. It seemed like a pretty logical statement to make. Doesn't seem like the accumulation of life's ingredients could occur in interstellar media like clouds and so on. And if people are happy with that, would like to make any changes to that, now's the opportunity to do so. At the bottom there, you'll notice that beneath this scary picture is a short sentence that says the early solar system was a dangerous, albeit promising place. And that's a kind of an opinion statement that came out of the strategy workshop on or over the summer. And is there anybody here who would like to take issue with that statement? I see no red flags coming up. why don't we explore that a little bit further towards the end of this presentation, and then I'll go to the next slide. So this, what we call the sort of operating motive of the strategy session was that Earth's rock record, we now know, since the last roadmap was formulated about 10 years ago, preserves materials older than about 4 billion years. And this, we say, constitutes the best available, or we could also rephrase that, the best direct record of conditions around the time that life emerged on Earth. And I think when we make that statement in the first sentence, we're not trying to impose on anybody the idea that we know when life emerged on the planet, but that 4 billion years ago, plus or minus a relatively small bit, is the area that at least we can explore from sampling campaigns. Now, the text goes on to say that the record holds our best chance for understanding how life came about on Earth, or even whether it was modulated or delivered from elsewhere in the young solar system. Now, that's a nod, obviously, to the supply of prebiotically interesting materials to the planet by comets and other primitive objects like carbonaceous chondrites, and even leaves open the possibility that life's genesis could have occurred outside and that the Earth was inoculated by organisms. When I put this text together, thanks to input from Steve Vance, also I'd like to say thank you, Steve, that although I don't accept the panspermia hypothesis for the origin of life, I don't want to exclude it altogether. And then next is bridging text that we discuss open questions in relating Earth's rock record to life's genesis and its subsequent evolution. Now, I see Max is typing something, but I haven't seen anything pop up yet in the open chat. So, Max, keep typing, because and Penny, thank you. Keep typing, and then as soon as you hit the return bar, I will be able to see. Aha. What about further input of more volatiles 100 million years later at 3.9 billion? Now, I'm presuming that Max is referring to the contribution of volatile elements and other compounds by the late heavy bombardment epoch. And that's something that I think is a rich area of investigation. People have looked at this from the point of view of modeling, and I think that those models, how some of which I've been involved in, however elegant, really do need to be substantiated by analysis of the rock record, and that could be something that we put on as an activity. And I agree with Max. I think that's important. Penny writes, even if one accepted panspermia, do you think we'd be able to actually distinguish this in the rock record? I share her skepticism on this point. And one thing that we could add, then I'll make a note of this to myself, both comments by Max and Penny, that all of the amazing work that has been done in the construction of phylogenetic trees, of course, and the attempt to take phylogenetic trees and link them to events in the past, geological events in the past, so linking biological events with geological events, that could probably be pursued with greater vigor. And I will add that to this to-do list that that's something we should look at. Any comments about that idea? Is doing a better job of linking what we understand about the phylogenetic tree, which is a representation of all contemporary life, not extinct life, to the geological record and to pay more attention to that. If you think it's a good idea, say so. If you think it's a bad idea, say so. Okay, I'm going to let you digest that. So we'll go on to the next slide. If I'm allowed to, there we are. So here's an outline. So it's solid materials rather than ephemeral records preserved in gases or liquids that act as a semi-reliable yet predictable and hence interpretable vault for information about the deep history of biology and planets. And I think that's appropriate for this part of the strategy document because we have been asked to talk about the rock record. And the rock record records input and output of planetary scale processes. And that's where theory comes in because nobody was around to see these processes occur, and geology is the quintessential science of circumstantial evidence. So we can never be absolutely sure, but we can use theory and observation to provide clues about things like planetary growth and evolution. Now, planetary growth goes back a little bit to Max's comment here about input of volatiles and things like seeding or fertilizing the planet from exogenous sources. But also evolution here, evolution in the planet's composition. Let me go back to the little green arrow here. This is something that, okay, let me try to get the arrow. Here we are. This is information here that is reliably recorded in the oldest rocks. Because anybody who picks up an old rock anywhere is concerned about its composition. Now, the composition of a rock is dictated by its original formational history and anything that's happened to it since. And geologists have spent the last 160 years so on working on such problems, and it's obvious, at least in this document, that we should take advantage of that scholarship. The next has to do with this term here, the oxygen fugacity. Now, there's been a lot of discussion here at the Gordon Research Conference, especially in the first day or so, on what exactly were the conditions for the emergence of life on our planet. And a lot of it boils down to our uncertainties out over things as straightforward and fundamental as the composition of the gases that came out of volcanoes that went into forming the atmosphere. And those compositions are dictated, for the most part, by the theoretical partial pressure of oxygen in the system. We have a good understanding of that oxygen fugacity for Earth's contemporary upper mantle, not so well for its lower mantle. This has been explored recently by some new techniques looking at at things like the partitioning of rare earth elements, which have variable oxidation states like europium 2+3+ and cerium 3+4+ in rocks and minerals through time. And others have done this, for instance, using nickel and chrome abundances in ancient rocks. But there doesn't seem to be the kind of consensus that we could reach if we perhaps put a little bit more focus on how the interior composition and oxygen fugacity in particular of the planet has changed with time. Well, this has direct bearing, obviously, on atmospheric composition. Now, if we can show something in more detail on specifics of gas species coming out of volcanoes and going into the atmosphere, and by models, and perhaps models guiding research and investigation of the rock record to look for evidence of such past atmospheric compositions, I think that's a major topic whether or not you accept an origin of life at the surface or in deep crustal rocks, sediments, atmospheric composition is something that I think we should be concerned about. Evolutionary innovation follows all of these things because it's evolutionary innovation by life that can be driven by a response to these changes in the geosphere, and furthermore, changes in the evolutionary innovations induced by life can induce changes in the geosphere. So this is the recognition that there's this coevolution then of the geosphere and the biosphere. Steve Vance writes, linking a rock record to phylogenetic tree is a good idea. It's difficult. The oldest rocks at best record only basic chemical remnants of life. Is it reasonable to hope we can link that information to genetic marker for the type of life produced it? And so my response for that is, yes, I agree with you. Having worked on these rocks and knowing how complicated they are, that indeed we can't hope to get genetic information out of them. However, it's this evolutionary innovation that I have a green arrow pointed to that may pave the way to overcoming that problem. Specifically, if we can find evidence for the emergence of a new metabolic style, like for instance oxygenic photosynthesis at a particular point in Earth history, we can say much like finding the fossil of an organism, that's not its first appearance, but at least that's its earliest appearance, and we can say it was sometime before that time that evolutionary innovation, like some metabolic style, like elemental sulfur reduction or disproportionation, appeared. How's that? Yes, Paula writes, I think it's possible, but it heavily depends on genetic marker and how we fully understand biosynthesis function, etc., in extant organisms. And Paula, you put your finger right on the problem there, because everything that we have in the phylogenetic tree of life is a record of organisms living at this very moment in time. Aside from valiant efforts at trying to reconstruct ancient genomes, it's all based on organisms that live now. So I think we have to work with that. Let's see. So Nikki is typing something, and if there are any other comments to make about that, I'll just go on now to the specifics addressed in each of these outlines. I'm not going to go into this, and you can sit self-explanatory. So I'll just go right to the first subtopic that was brought up in the workshop, and that is the composition of the early atmosphere. And the participants initially decided, well, we should probably stick to the first 2 billion years. That's the part of the ancient atmosphere that we know the least about. So there's a lot of exploration to be made here. The discussion begins then that the rock record holds our best available constraints on atmospheric composition and pressure. Now, life today operates symbiotically with this atmosphere, maybe cybernetically rather than symbiotically. It seems likely that this was not always true. Now, questions that arise from a discussion topic like that include, do the Earth's oldest rocks record the atmosphere present when life first came about? And my answer is no. What we end up seeing is that as far back as we go, before the sedimentary rock record runs out, there seems to be some activity of a biosphere. Does that period bear the strong imprint of life? I don't think that that has been resolved. In fact, I'm not aware that it's been explored much at all. What I think is meant here by the idea of strong imprint of life hinges almost entirely on disequilibrium atmospheric chemistry that might be recorded in a mineral phase, such as a sulfide or a sulfate. Now, what would we look for? this seems to be an area that potentially holds an enormous promise. So besides looking, for instance, for sulfur isotope anomalies in ancient rocks, that we could try to investigate maybe other evidence, lines of evidence for the early atmosphere that may be preserved in robust mineral phases. Nikki writes that she's not a molecular biologist, but linking the timing of events in the rock record to radiation of organisms in trees is hard, because it's hard to get a sense of absolute timing in trees. Correct. That's where geology comes in and provides absolute ages. You can't just plot dates in a tree, as occurred in a publication in 2003. Well, there's another publication I know of, a famous one in 2001, that attempted to do that with, for instance, microbial sulfate reduction. But again, I mean, if you can find evidence for that kind of microbial activity in a rock that an absolute age can be determined on, then what you're getting is a minimum time for the appearance of that particular metabolic style. It wouldn't tell you necessarily what the organism is, but it'll tell you the metabolic style. So I think with that kind of caution, none of these documents ask people to throw caution into the wind, but as astrobiologists, we're brave enough to try. And so I think that's an important point that Nikki brings up. What is the record of early climate? There's been some pioneering work on atmospheric pressure, most famously on the imprints of raindrops and so on in ancient sedimentary rocks. But there may be some other techniques to try to get an idea of whether or if atmospheric pressure has changed significantly with time. That I would say greater than about 10%. And whether or not there's been very, very large swings in temperature of the atmosphere, including associated with the snowball Earth events. Now, question number 3, here we are. Penny mentions that there's a difficulty in attempting to infer partial pressures of important gases, complicated by uncertainty of internal differentiation, outgassing planet interior. Well, I like that point that she brings up. What is the uncertainty about internal differentiation? I think that timing of that has been pretty well established, but maybe part of the problem here is that different communities are not communicating to one another in an adequate fashion. For instance, in people who are working on things like the long-term radiogenic evolution of Earth's crust, a consensus is growing that differentiation happened quickly and early on our planet, and even earlier on a planet like Mars. Mars seems to have completed its differentiation into different silicate reservoirs approximately 3 million years after T0. Now, on the Earth, even if that did happen, subsequent events like the giant impact into the formation of the moon would have caused a reset of that, and then creation of new silicate reservoirs. Penny acknowledges that deep Earth folks are not talking to others, and let's pull the troglodytes out and have them talking to the rest of us. And I would certainly like to see that happen more. Can we get specifics here, subpoint number 2, on the partial pressure of key important gases such as nitrogen, CO2, hydrogen, methane, ammonia even, oxygen, sulfur dioxide, hydrogen sulfide, etc. How can we hope to do this? Historically, people have invoked stable isotope mass balance arguments as a way to get to these answers. I think, for instance, of beautiful paper by Manfred Jalowski in 1975, who first said, look, in order to account for the difference in carbon isotopic composition of carbonates to organic carbon in the crust over geologic time, you had to have a shift then from a 9-to-1 ratio of carbonate carbon to organic carbon to more like an 8-to-2 ratio once the biosphere was taken over principally by oxygenic photosynthesizers. Now, how else might we get that? This is where things more like investigations of the rock record and sediments in the rock record would be worthwhile. And this is old science. I mentioned that paper from 1975. Well, there's other work by Preston Cloud and Dick Holland and even earlier W.W. Ruby in the 1950s. But the problem has never, in my mind anyway, been resolved to the point where we could have a synthesis of these ideas into some kind of a review. And just once again, I think we're not going to be able to do that unless we have the deep earth people working on mantle geochemistry talking to those who are concerned with the surface zone. And then point number 4 here is that this information obviously feeds into how we understand the oxidation state of Earth's mantle, as I mentioned previously. Then, of course, the role of hazes in climate modulation. This is a topic that seems to rise and fall now and then. But one interesting thing about hazes, of course, is that they are sediments from the air. So hazes are aerosols, and aerosols can be incorporated into the rock record as part of the process of normal sedimentary process. So what sort of work is being done on looking at the record of hazes and the role of hazes in climate modulation? Most of it is modeling, but there's some folks carrying out analysis in ancient rocks looking for this sort of thing. It seems to me that's important because many climate modelers and atmospheric physicists point out that hazes can both cool and warm the planet depending on the physics of these hazes. And we know that from a possible early Earth analog, the moon Titan, that hazes are just about everything in a place like that. Now, formation of prebiotically important molecules might arise out of this kind of haze chemistry, and the appearance of new metabolic styles like oxygenic photosynthesis could wipe such a chemistry out. And I'd like to mention, because this has been talked about at this Gordon Research Conference a couple of times already, that this sort of appearance of metabolic styles and changes made to the atmosphere is just the kind of thing we'd be looking for by remote analysis of exoplanets. So what can astrobiology contribute to our understanding of the analysis of exoplanets? Well, I think it starts with this kind of work here in sub-theme 4, and also more of the modeling work about how planets are built in the first place. So that concludes presentation on that slide, and unless anyone would like to make comments at this point, I'll continue to the next slide. None? It's perfectly clear. Okay. let's go. Right. Clear as haze, right. So far all of you are unhazed at this presentation. So how about water and life? This then moves us from the atmosphere discussion now to the hydrosphere. And you may be wondering at this point, where does Earth's earliest rock record fit into discussion of atmosphere and hydrosphere? And I would argue as a geologist that you can have atmosphere or hydrosphere without the rocks, because it's if you have degassing from a planet, of course the ultimate source is going to be Earth's mantle, with perhaps some supplementation from exogenous sources like comets and so on. But it's that flow through and then the subsequent interaction of hydrosphere and atmosphere with the geosphere that I think the rocks actually govern. So Earth's earliest rocks tell us something about the composition of the early ocean, which may or may not have been more saline than the present day. This has been a topic much discussed, especially a few years ago, but seems to have gone dormant, and I think maybe we need to pick that up again. We don't know whether the first life operated in freshwater or saline conditions. Most people take it for granted that it's saline conditions because we think of a marine origin of life, but as long as you have dry land, and I think that's one of the key features over here to this freshwater versus saline condition, you may have freshwater pools or oases. We actually do not know that. Did life form or emerge under deep or shallow water conditions? We don't know the average temperature of the ancient ocean. There are three camps, the high, medium, and low camp, I like to call them. It's time for us to put these people together in the same room and tell them you can't leave until some kind of consensus or plan to reaching consensus is made. A good deal of ink has been spilt on this topic. Yes, I would say a workshop bringing together deep earth folks and astrobiologists makes sense. I would be the first person to sign up for such a thing because I think with such a meeting, we could do things like say whether or not there was significant dry land around that could provide Darwin ponds or however you want to call them. And what about let's talk about it after. Okay. I share your enthusiasm. Has the surface volume of Earth's oceans been more or less the same in the past 4 billion years? The first talk of this Gordon Research Conference proposed 8-kilometer deep oceans. That requires an increase in Earth's surface ocean volume if you take away hypsometry of about a factor of 3.5. We can account for geochemistry by summing up all of Earth's ocean water, what's locked up in ices and sediments and hydrated crustal rocks, and we come up with about 2.2 ocean volumes of water. But Earth's mantle has a storage capacity of 11 ocean volumes, and the Earth's core has a storage capacity of several hundred ocean volumes. So, has the surface volume of Earth's ocean been more or less the same? Well, I'm sorry about, it should be partitioning, not portioning. So that's probably something that's governed by long-term partitioning between the hydrosphere and mantle. This is something that deep Earth geophysicists, geodynamicists, geochemists are working on, like how dry is Earth's upper mantle, and then is it being replenished by erosion of Earth's surface ocean by subduction into the mantle and mantle hydration, or is it mass balanced? Now, there have been arguments based on analysis of the ancient rock record that maybe Earth's ocean volumes were substantially greater, like by a factor of 2. I don't think that this is widely accepted, but it's certainly worth investigating further. Now, some questions that arise here. What do the oldest rocks reveal about ocean composition of Earth when life formed? Do we have a reliable and interpretable record from that time? And how far back can we go? And Penny notes that Kent Condy, who's a great colleague, is one of the world's experts on early continents, and Ken should definitely be included in any such discussion with many names that one could come up with. Michael points out that he ought to have time to do this sort of thing. Yeah. No, Kent is a dynamo. How far back can we go? Well, as somebody who works on such things, this is a big question. I don't know. A lot of that is determined by the availability, i.e., the presence of rocks that are of marine sedimentary origin. And I'm going to throw in a little bone there and say that is something I think ought to be an interesting and important avenue to pursue. It's like try to improve our inventory of ancient rocks. Now, I heard some noise over my headphones, and if someone is trying to talk or engage in the discussion. No? Okay, maybe it's just some interference. Yes, I heard that. Hello? Okay, we'll just move on. Does the rock record tell us whether life arose in a freshwater or oceanic environment? Now, there's been some interesting work, past work, on trying to determine whether or not some of the rocks that we have in the old record of the Earth actually formed in a freshwater environment or not. There's some indications that there are lacustrine sediments, lake sediments, that are very ancient, but almost everything we have appears to be marine. Can we get specifics on average seawater pH, things like magnesium-calcium ratio, phosphate content, iron, cobalt, nickel concentration, and so on? This is the kind of, Nature, Science magazine type stuff. If you can give Earth's seawater pH 4 billion years ago, I assure you that would get a lot of people interested. I have read in the recent literature a range of seawater pH estimates from 1 to 11, and that's just in the last 12 months. Yes? Okay, so Michael points out that another line of evidence comes from ancestral reconstruction of biological activity in different pH conditions and particular biological enzymes that are pH sensitive. Now, so what this does, of course, is it gives us the opportunity for another cross-linkage that wouldn't normally happen except under circumstances like this. So how about having molecular biologists talk to people who study the record of things like seawater pH with time? Penny points out that 11 log units narrows it right down, and I agree with her. Now, the next point is that this information feeds into how we understand things like oxidation of Earth's mantle, role of hazes, primary, and again, new metabolic styles that go back into water and life. So the hydrosphere and the atmosphere are intimately linked. Okay. If you want to contribute, click raise hand, and then we'll call you on the cell. Okay. Good. I really like this open chat here. It's fantastic. So let's go to the next slide. I see we have 17 minutes left. What was the fate of the first crust? After planets finish forming hot, they end up with a rind, and that rind on silicate worlds is rock. On icy planets icy worlds is ice, and so this platform has to almost immediately undergo some kind of transformation. The transformation on an Earth-like planet is going to be between the crust, the hydrosphere, and the atmosphere. And planets must lose heat. This is something that no one can disagree with. And the way the Earth loses heat is three ways: by conduction through the crust. First of all, it's convection in the mantle, bringing the heat towards the surface. It diffusionally conducts through the crust. That's not a good way because the Earth's crust is a good thermal boundary layer. Second way is by plume activity, which might be one of the most common ways planets lose heat in the universe, because it doesn't matter really what the behavior is and some of the mechanical characteristics of the thermal boundary layer. Heat builds up and will punch through it, and heat is lost that way. That's probably the primary mechanism of heat loss on Mars and Venus. And the third way is, of course, on Earth. It's plate tectonics by ridge volcanism, 60,000 kilometer long operating volcanic mountain chain, and subduction. So that crust gets subducted and acts like a cold finger. Mary points out that understanding Deep's past, National Research Council report would be something that we should add to our list of references in talking about that. Japanese LC has a strong component studying Earth's deep interior, as Steve Vance points out. John Hernland and Hide Genda come to mind as people who contribute. Both great thinkers, Genda and Hernland. And thank you once again for pointing that out. Now, Earth's oldest rocks are, on the face of it, peculiar because they're dominantly felsic. They're granites and granitoids, rather than what you would expect if you took a molten silicate planet and then cooled it at the surface, things like basalts or basaltic canadites. And that's peculiar at first, but then you realize that basalts and other mafic and ultramafic rocks are very, very reactive in the presence of water. They are stable compositionally in the Earth's deep interior, but once you soak them in water, it's all over. They serpentinize and they increase volume by 30%. They become mechanically weak and subductible. It's really and the felsic rocks are the distillate of that process during the subduction of these mechanically weak crustal components. And so that's probably why we see them. They're thick, buoyant, relatively unreactive, and compared to basalts, and that's why we have these things. When the first crust formed, it was in the context of occasional giant impacts, and this first crust seems to have been destroyed because we have no evidence of truly primitive extinct radioactivities in any rock that I'm aware of that's younger than 3 billion years. So that means that this recycling and reworking has resulted in a kind of homogenization of what was originally a highly heterogeneous planet from initial silicate differentiation. Now, continental growth is a consequence of cooling this planet in the presence of a watery veneer. How has this changed with time? There are people like Chris Hawksworth and Bruno Dume and others who've pointed out that along with the change in heat production of Earth's interior, you see a rise in continental volume and a change perhaps in tectonic style. Again, this goes back to Ken Condi, who's been thinking about this for many years. Now, what might we expect to have happened on other planets that may have had watery veneers and this kind of heat loss mechanism, like Venus and Mars? And one of the points I tried to make at this meeting was, let's not ignore Venus. Venus seems now to be Earth's evil twin sister, but it seems to have had a more peaceful and procreative past. Why are the oldest Earth rocks felsic rather than mafic? The late heavy bombardment on the moon and other worlds should have affected Earth's early crust, but what was the duration of this bombardment? What evidence might exist for this epoch? It's a topic that actually keeps popping up here at this Gordon Research Conference on Origin of Life. And anytime anyone shows a time scale, there's always this sort of blowtorch symbol at right about 4 billion years ago. So I think we need to understand that better. And evidence for its duration is almost exclusively from analysis of lunar rocks. However, there are some interesting opportunities coming up now from analysis of the ancient Martian surface from the Mars Science Laboratory, as well as from a new class of Martian meteorites, the Martian regolith breccias, that were only discovered in 2011 and have been the topic of enormous research efforts in the last 12 months. Finally, duration is also constrained by dynamical models. So the kind of work that people like Hal Levison and Alessandro Morbidelli and Simone Marchi are doing to try to understand how you reconcile this lunar record, stuff we get from asteroids, maybe early Earth rocks and Mars, with how planets grow and evolve and migrate through. It's all about gravity, as Hal would say. Can we get specifics? Here's point number 3 in questions on the volume of continental crust and dry land, and when did crust-hydrosphere interactions first take place? Because, you see, any world that has hot rock and water will have hydrothermal activity. Hydrothermal activity is something that has been a central topic to astrobiological research. But now what we're hoping to do here in this part of the strategy paper is to put that in a more planetary context. And then how did this govern the composition of the oceans and atmospheres? Can we narrow down even further the possible pH range of the ancient oceans from 10 log units to maybe 2 log units? Let's say that's a challenge. What was the fate of the primordial crust? Why did it take so long to vanish? 1.5 billion years is a long time. That's many supercontinent cycles in the contemporary Earth. And finally, are there yet older sedimentary rocks awaiting discovery? Where might they be found? And as I mentioned on Monday morning, all geologists should hang their heads in shame, because every ancient rock locality that's ever been discovered has been stumbled on by accident. And so it's time for us to change that trend. Now, going to the next, now we have 8 minutes left according to my schedule here, and this is a perfectly opportune time to solicit questions for the next 10 years, things to work on, connections with other astrobiology themes, and what I've missed here that you think is important. So I open the floor. Okay. We have a question here from a member of our audience at the GRC. Okay. I see. So the question is, let's add to this shopping list of things we need to know about with ocean composition. Let's not forget things like uranium content, and if you go back far enough, plutonium content. It turns out this is interesting, plutonium is highly soluble in water, and it would have been present in the early oceans, but we don't know what the concentration is. But that is something that's calculable, because a paper in 2005 we published on the xenology of Hadeen zircons. We found plutogenic xenon in there, and so it showed that the Earth has a chondritic plutonium-uranium ratio when it began. And so knowing what we know, thanks to Department of Energy and so on about the solubility of plutonium, we might calculate something like that. So the point, the overall point was, what was the radioactive load of the oceans, and would that have been significant? Okay. Penny writes, I think the super early history of water as expressed possibly in zircons is critical. In my deeply biased opinion, I completely agree. And that is something that I know of at least six or seven research groups that are tackling right now. And I think that we could say that work is ongoing, but maybe it's time to find new lines of evidence too, that we don't just hang our hats on the oxygen isotope and zircon story, but try to find other things, like, for instance, mineral inclusions in these ancient zircons. Some of them seem to contain hydrous components. Now, are these representative of the melt environment in which these ancient minerals crystallized, or are they some kind of late addition, like a contaminant? And that I certainly appreciate. Other questions and points to bring up? General question here from another member of our GRC community.
Oh,
okay, here we are. Go ahead.
Yeah, my question, as I said, is just a general question. If we're looking for life on different planets, and obviously there are different environmental conditions, are we looking for, since we're in this conference, looking for, I guess, life, could it have also started independently in different environments here on Earth also?
So there was a bit of an echo here, but your question was, could life be generated could life have been generated here independently on Earth in different environments simultaneously? Okay. So that is actually the heart of a recent paper that appeared in the journal Geobiology by Eva Stucken. It's a big review paper, Stuecken. And in that paper, she tried to put together all of the different scenarios that had been described for prebiotic synthesis and early life environments in every different environment for life. And Eva's conclusion was that a planetary scale chemical reactor like the Earth requires each of these different sort of interlocking mechanisms in a kind of crustal plumbing network. It's a very nice review of more or less what are the different sort of terrestrial environments that you could get prebiotically interesting molecules out of, and perhaps even the first life. And so that might be something that we'd have to add to this document because of it being so comprehensive. Yeah, just appeared in Geobiology about a month ago. Yeah. Yes, we have another question. Okay, so prebiotic chemistry in some scenarios requires particularly dense solutions of amides. Mm-hmm. So in other words, we mentioned nitrogen extremely briefly at the beginning of this presentation. What more can be said about nitrogen chemistry that leads to the origin of life? And people have, again, this is another thing that that has been one of those topics that people have looked at, but maybe we should redouble our efforts on a little bit. What are plausible prebiotic sources of biologically useful nitrogen compounds? Because N2 wants to stay as N2. Tragic as that is. Now, and so perhaps improving our understanding of that inventory of reliable biologically available nitrogen is something that we should look at in the context of the rock record. There was a lot of interest in phosphate, and a beautiful presentation by Matt Pasek on this topic, but nitrogen should be included in that. Yep. Steve, how can we get better at finding ancient provinces on Earth? Can remote sensing help? Imagining hordes of students scouring Google Earth imagery. Well, my response to that would be, unfortunately, although the coverage of Google Earth is great, but its resolution is not so good. And by looking at a terrain, you can't tell how old it is. You actually have to go there. But I can tell you stories best discussed over dinner or something about how many times when that a funding agency has, if they whiff something that they construe as a fishing expedition, they back away from it. But sometimes, just to carry on Steve Vance's point, fishing expeditions yield fish. So, maybe it behooves us to have a slush fund. You didn't hear me say that. To fund not hordes of students scouring the Earth's surface, because they would probably get drowned or eaten by bears or something, but instead doing traverses over terrains that are otherwise poorly known, but we have a fairly good idea of their antiquity. That frankly speaking, aside from mining companies who do this for, I'm not saying I'm a capitalist through and through, but for purely resource reasons, we might consider doing such a thing in our science. Now, Max says, Steve, nice and stimulating presentation. Thank you, Max. Sorry to go. He has to go to another meeting. Look for other volatiles that might come from the LHB. Together with water, coexist in oceans. His favorite is chlorine, and chlorine isotopes could be preserved in rocks. Max, excellent point. From my knowledge of chlorine isotopes, little work has been done on ancient rocks. I know it's something Zach Sharp is looking at UNM. He's one of the world leaders in chlorine isotope geochemistry. And I've sent Zach some samples. We'll see if they bear fruit. But this is, I would add bromine to this, and some of the other halogens and halogen-like elements. And but as far as I know, the chlorine isotopes for Earth materials are they more or less yield all the same chlorine isotopic compositions. It's only once you get to lunar rocks, as Zach pointed out, that you find any kind of significant variation in chlorine isotopes because of the absence of hydrogen. But this is the kind of thinking that, I think it's worth pursuing. Noble gases also, people like Igor Tolchtikin and Bernard Marty and others have used noble gases to try to tease out whether or not part of Earth's atmosphere was supplemented by later significant meteoritic addition. And these are the same people who, by the way, also think of deep Earth problems. I see we're just over time, but everyone here is well fed and seems well hydrated too, and I'm game for continuing. Is there anything that you think it's a glaring omission from all of this? There's been no talk of the great oxygenation event, the record of that. There's been no talk of the takeover of biogeochemical cycles by life. For instance, the takeover of iron in the oceans, nickel, cobalt. How about it might be the discussion for those of you on Adobe Connect here that can't hear this. Mary and Lindsay pointed out that there's most of the emphasis at our strategy meeting, at least for the geological record stuff, is focused on the very early record. Now, folks who were at that meeting who really concern themselves with such things include Tim Lyons and colleagues. And my understanding was that they were working on something like that, but I wasn't directly involved in any of their subgroups. But they should definitely be linked in with us on this document. Mm-hmm. Okay. Well, well, you know, that's what I get paid the big buck for, right? No, seriously, the discussion here seems to be converging that we should include the takeover, the study of the takeover by life of the biogeochemical cycles with an eye on the great oxygenation event. And that doesn't, as Penny points out, that doesn't fall within the scope of the earliest rock record, but depending on who you talk to, a rock that's 2.5 billion years old is part of that earliest rock record. So we could change, it's easy to change the title. Yes, we are too late in the process for us to stand up another group that, and we should integrate that topic into one of the topics within this theme. Okay. Is there, shall we say that there's consensus on that? Get more help, yeah. Right. Anything else?
Okay, you want to start talking?
Good, yes. Let's get Steve Benner on the line here.
Yeah, I mean, so I'm assuming that you've already gone through it because I'm late, so that's the first thing I should say to whoever's online. And therefore, I'm not allowed to have any opinion whatsoever. But if you've gone through the idea, we want to know the water inventory, the solutes inventory, all these kinds of questions which are extremely difficult to get at.
A lot of it might be gotten out by planetary comparisons, right? Certainly Mars is a way of, and that's all been covered, right?
Yes.
Okay. And so the other things, of course, in nitrogen, the elemental abundance, but more there, the redox state of the inventory, since if it's all right. So, but presumably that's something that you've also already covered. So,
that's high on our priorities list, actually.
Yeah. So now the question about reconciling trees, molecular trees, well, did we decide that we understand the problems with the molecular trees, and that is that you are all, instead of interpolating, you're extrapolating, and since you set your clock rate.
Yeah.
Okay, well, the issues are fundamentally that you have to calibrate your clock, and so the clocks cannot be, no nucleotide clock really can survive that far back in the geological history. So there are always protein clocks. Everybody knows that the amino acid substitutions in protein clocks are episodic, that it, as function is created new. What's quite clear is that if you calibrate the clock over the last billion years of history, that clock will be running slower at the protein level than in the first billion years of history, if only because in the last billion years of history we at least know something of want to have by way of protein sequence at the beginning of the episode, whereas at the beginning of the first episode, presumably there's been rapid sequence. So almost all these clocks do not extrapolate linearly back, and this is a well-understood phenomenon as to why you end up having clocks saying that life originated on Earth 6 billion years before the planet started. And so, so I mean, that's an intrinsic problem. I mean, part of it can be managed by a lot of these resurrections, which you heard from Eric Gaucher and these people, and try to at least, or what Andre Lupas is talking about, you can try to do some of it. It's going to get you back to, well, it depends on whether you believe in the RNA world. If you do, it's going to get you back to a relatively recent biosphere, one that's not really close to the origins at all. So, I mean, I don't think that reconciling the clocks is going to be a big problem or a big priority, because we know the problems with them. We know how hard it is to reconcile, and even if we do reconcile them, we're not going to get a good beat on origins. Now, I'm speaking of origins going to come. I should not be doing that. We should be now talking about astrobiology, which is a whole different question. Of course, for the more recent evolution of life, this becomes a very important problem, which I should not dismiss.
The important points that you bring up, from the point of view of geology, of course, is something that we might conceivably be able to tackle if we can pin, using an absolute age of a rock, where there is evidence for a particular metabolic style.
Right.
So it's simply finding an earlier form of Archaeopteryx.
I have made
that's that diversification time, at least.
I have blundered because I have been answering your question in my role as the Origins of Life Gordon Conference chair. Astrobiology is quite a different question. If you can now interpolate clock rates, which you certainly can do, and you can say, for example, how ribulose bisphosphate carboxylase responded to a changing atmosphere at a time where the correlation between the clock date and the geological record for when oxygen arose, for example, this would be adding. And of course, Gaucher has done a lot of work where he's worried about the temperature in which endosymbiosis occurs. The temperatures of early Earth I know you have the, Paul Knauf and Low data arguing that there's a very high ancient temperature to correlate anything in the global temperature regimen to understand why oxygen 1816 isotope ratios are not reliable, why they're wrong. I mean, people like Casting says these folks are just crazy, right? But absolutely, to be able to interpolate clocks, to get those precise, and then to go back and do, in an astrobiology sense, not in an origin sense, build a cross the biosphere sweep connecting the history of proteins to the geological and mineral record history, and then, of course, the fossil records. That would be tremendously important for astrobiology.
That's good. That's very satisfying to hear, because, I think we're all on the same page with that. Yeah. We have a hand up here. Armin.
Yep.
Yes, that would be good.
One more contribution from biology could be to exploit the fact that many proteins and also RNA complexes, they contain inorganic ions as catalysts. And just by choosing those proteins that should be very old, evolutionarily old, and checking on which ions they functionally depend, it's possible to reconstruct, predict the environments where the first organisms could survive. And this is one more constraint, because the very first organism, per definition, could not keep their internal chemistry quite different from external chemistry as modern organisms do. And therefore, the inorganic ions that were trapped by their enzymes should have been present at their habitats. And it also provides some information, and that's what we are doing for the last several years.
Now, that's an interesting point, and there's been a discussion on just this sort of thing. I think about, for instance, people like you and Nisbet and Norm Sleep, for instance, put together a review paper in Nature, and a Nature article about a dozen years ago, where they made such an argument based on, for instance, the presence of chrome, tungsten, nickel, cobalt, iron as important ions and catalytic centers of fundamental protein enzymes. Now, they immediately pointed out that such metals are extremely abundant in seafloor type rocks like basalts and basaltic komatiites, just the kind of rocks that we would expect to form at the bottom of the ocean in actually at any time. They're forming right now. Lost City and so on is such a strongly modulated hydrothermal system by the composition of the rocks that are being hydrothermally altered that are so rich in nickel, cobalt, and iron, but not so much in zinc and manganese and aluminum and potassium. I like that kind of synergy.
The point is, if you limit yourself to the proteins which are really old and were present in the last universal cellular ancestor, definitely were there because they are present in all living organisms, then you find quite the opposite. You find that concerning transition metals, they depend on zinc and manganese and not on iron. And in addition, some of them, and the most importantly, the translation factors, protein synthesis machine as a whole, they require high levels of potassium, and they are blocked by sodium. And altogether, it might indicate some kind of freshwater environments or something of this kind, and not marine environments. So it's one more set of constraints that should be kept in mind.
All right, that has a natural home in this takeover by life of the biogeochemical cycles topic. Yeah.
Well, I guess the question actually for the NASA people here, you do have the Tree of Life, right? And that does NASA participate? You fund that. Oh, no, I understand. Okay, no time for levity here. So does NASA fund any of that, or is that okay? So the point is, you do have this genomic now picture. Is there a geology parallel now trying to tie to the Tree of Life? This is all this side of 2 billion years, so you might argue that it's not really relevant to origins. But is there a NASA activity right now, or a geological community activity which would go through the Tree of Life? So, you had shows, though, talking about visual pigments and the origin of vision. Now that's the last 100, 200 million years. So it's not a very deep astrobiology problem, but there would be, in principle, geological correlates as to how much carbon dioxide there is in the atmosphere, what's the color of the fruits and plants that they're interacting with. The fossil record would maybe go. Is anybody doing that?
Well, this is, of course, it's funded by NASA programs such as the Exobiology and Evolutionary Biology program.
Right.
But is there a
geologist involved? Right. So does anybody go back to the Ordovician extinction, look at what went on, and then, that's a fossil record, there will be a geological support of that, and then go back to the tree of life and see what's going on at that time in terms of gene duplications, gene losses, gene...
Not
right there.
Not that I've seen in the literature, and it's something that I try to scan regularly, but
because
that doesn't mean it's not there.
Yeah, because in a sense of what we did with elongation factors, and which Eric has carried forward, is that, right? So we have desperately been missing the geological correlate. So Eric has a temperature history through time, for which there's no real geological. I mean, the only person who got interested was Paul Knauf, because Eric's most deepest ancestor, roughly aquifex diverging from other bacteria, was at 65 degrees, and his isotope record said 65 degrees for these ancient sediments on a global-wide ocean, I suppose. But that would be something that, it's ripe to do that now. Whether anybody's interested in doing that is another question. And Mike, you say no, right?
Yeah. But for Phanerozoic stuff?
Well, I mean...
Because I can name people. There are a number of groups, for instance, in Europe that are looking at, for instance, biochemical cycles and all of that in the Paleozoic and that kind of thing. But stuff that's going on in the Proterozoic, that's mostly the domain of workers such as Don Canfield and Tim Lyons and Ariel Anbar and Kurt Kornhauser and others that are funded not just by NASA but by also different other federal agencies and institutes. So how does that feed in to this? That I would say that we should tack ourselves on to those very active and vigorous programs and learn more about what they can tell us about putting time, absolute time, on the tree of life. I think that's what people like Ariel are trying to do. Yes. Mm-hmm. Yeah.
Well, I mean, this is somewhat speculative, but the time is ripe, right? I mean, genomics is ready; it's past ready in some sense. So, but I've never actually seen anybody either. For example, the oxygen level in the Jurassic is supposed to be higher than today, right? Which means the hemoglobins of birds living, Archaeopteryx, should have a different, physical biophysics. So I've never seen anybody say they're going to resurrect the Archaeopteryx hemoglobin and see whether it correlates as a proxy with the oxygen atmosphere content. I mean, I do know that Eric would very much like to have a geological temperature scale, which people put together, right? And they just disagree about it, right?
The BLAG model is the canonical model for that temperature scale. The Berner-Lazaga-Garrels model using carbon isotopes, and we get CO2 partial pressures and oxygen partial pressures throughout the Phanerozoic. And before that time, that can also be done. People have been working on that.
But you would standardize it in the Phanerozoic, and then you would use the biochemistry as the proxy to perhaps resolve ambiguous geological records in the Proterozoic. That would be the kind of thing that people would do. There's only one right? And eventually, this is bounded. In 10, 20, 30 years, you can imagine a reasonably complete, like the periodic table, you're going to imagine a reasonably complete model that couples geology to genomics. And then, after 30 years, that it will be pretty well worked out, and then you can move on to other things. It's fun.
One example that Nikki points out is Brock's trying to reconcile lipid biomarkers in the tree in the 03 paper. That, of course, has run into problems because we now, by Brock's own admission, that that's probably mostly mobile petroleum and contaminant. But progress is being made, and it seems to me like that might be low-hanging fruit to try to tackle the problem of seawater temperature and maybe even pH for the Proterozoic and earlier into the Archean. If we can do that, that would be
exciting. Should I push the mute button now?
I see that we're at 2:24 p.m. Is there? Thank you, Steve. Anyone else here would like to? Okay, so I think that might be a good place for us to stop. And I want to thank you, everyone here, for attending. I want to thank the folks who helped put this together, Mike and Andy, and Mary, Lindsay, and Mike, and thank you, Penny, for participating in the discussion, and all of you here. And so the next step is to put this together into a growing document, which will be available for more public comment. Thank you all again.
Thank you, Steve. And this video will be up on the website probably tomorrow or the day after, just in case you want to reference it for anyone. Thank you very much.
Okay. Yes, thank you. All the best now.